So I begin, and what about your questions, remarks? No? Yes, Bob.
There is the physics literature on all of this, and they always call the little v's in our representation space, they call them the states, and operators act on the states. But with the joint operator, then isn't the Lie algebra is acting on itself?
You know, it is better if you ask some people who pretend to be physicists, like Albert Sports, and probably will get a good reply. I can say something, but you shouldn't believe me. But you're right. Yes. The elements of a modular or Lie algebra are called states in physics, in something which is called physics. Maybe not physics precisely. And certainly there is a whole dictionary which translates words from representation theory, differential geometry, whatever else, algebra, from mathematics into physics and back. I know some of this dictionary, but certainly my knowledge of this is not full. So today, my lecture today is actually the last lecture, as I hope, about the classification of simple Lie algebras. Whatever I do not say today will remain unsaid. I will formulate some exercises, but mostly it is all good. You remember what? All done. So first of all, we have a reliable classification of all possible systems of roots. We express the result in terms of the Dinkin diagrams. What we don't have constructions. So we know that for any, say, simple Lie algebra, complex simple Lie algebra, its root system falls in our classification. That is, there is a Dinkin diagram which corresponds to this simple Lie algebra. What we don't know, or pretend that we don't know, is that actually it is invertible. That is, for every admissible system of roots, there exists a real-life complex Lie algebra which has this system of roots. This we will do partially today, and I will comment regarding the rest of it. And also, we have a theorem which was almost proved last time. I will make some final comments about the proof today. That if two complex simple Lie algebras have the same system of roots, what does it mean? It means that there exists an isometry between their Cartan subalgebras, which takes roots into roots in both directions. In this case, the Lie algebras are isomorphic. And there is an isomorphism which is constructed. Now, the construction of this isomorphism was almost done last time. I will just one last remark. I had to say this very briefly last time, so I will repeat what we do if I find some chalk. Yes. So we have two complex simple Lie algebras, G and G prime. We have an isomorphism between. By the way, this notation prime, I use it, which is certainly should be prohibited because we use the same notation for the commutator subalgebra. All I can say is I apologize. Such ambiguity of notations. So we have two Cartan subalgebras, and isomorphism between them. Isometry, it has to be isometry if I say that it establishes correspondence between roots. I mean, rather the isomorphism with dual spaces. So we have sort of the same roots with the same inner product, the same everything. Then these Lie algebras are isomorphic, and we construct an isomorphism between them. We actually do slightly more, but this I will comment. So, first of all, for every non-zero root alpha, we fix an E alpha in this one-dimensional space, and the only condition which I impose minus H alpha, or the inner product of alpha and negative alpha is -1. Let me write H alpha, and well, you know what it means, so I will not repeat it. This is not unique, because we multiply E alpha by some number. This should be true for every alpha, but we multiply E alpha by some number, and for positive roots, and E negative alpha divide by the same number, then certainly this condition will still hold. Still I fix these things, and then if alpha plus beta is a root, and this should be proportional to E alpha plus beta, and I denote the corresponding coefficient as n alpha beta. If alpha plus beta is not a root, then I simply put n alpha beta be 0. Actually, it's not important. I can take some other value. Okay? Okay. Now, I want to choose E prime alpha in G prime alpha prime, which have the same, this E primes should have the same properties, all the written here. How to do that? We have some relations between n's, which I will not list now, but I will use one of them. Up to some time, this goes very smoothly. I use induction. For this purpose, I take the natural ordering of the roots, of positive roots, of all roots. This is according to the distance from the hyperplane which divides positive and negative roots. So I suppose that all these distances are different. It is certainly easy to achieve using this plane somehow. And now I suppose that everything is done. Everything is what? That for every alpha, which is between negative rho and rho, where rho is also some root, some positive root. This means, you see what? We have ordering of roots. For every alpha, we already have E prime alpha. And then if alpha beta and alpha plus beta all satisfy these conditions, then E prime alpha, E prime beta commutator is the same n alpha beta times E prime alpha plus beta. I should put prime everywhere. So I suppose this is done. And then I need to make a step of induction. What does it mean? I need to extend this to the roots rho and negative rho. Just one step. Rho and negative rho do not belong to this community, right? They do not satisfy to this because this inequality is strict. So I take rho And I want to choose first this. How to do this? There are three cases. First, that rho is not alpha plus beta for positive alpha and beta. You understand? So rho is a simple positive root. Then I choose E prime rho in an arbitrary way. Then E prime rho is arbitrary. And we do not need to care about this because the equality alpha plus beta is rho never occurs. Second case, which is more interesting but still very simple. When rho is alpha plus beta for a unique pair alpha and beta. Again, in this case, I don't need to do anything because I just, I already have. So first I define this as n alpha beta E prime alpha E prime beta. It is rho prime I need to write, excuse me. All these primes. And that's all. And my condition holds for the same n, right? And then the only case when I actually need to do something is the case when this pair is not unique. So let rho be equal to alpha plus beta and also to gamma plus delta. And the sets, these pairs, the sets of these summands are not the same. So alpha is not either gamma or delta, and beta also is not either gamma or delta. Right? In this case, my definition becomes ambiguous. Certainly, I have again E prime rho. I define it using alpha and beta. I still have E prime gamma and E prime delta. And this should be proportional to this because both belong to the same one-dimensional space. But the coefficient is some n prime, gamma prime, delta prime. And I want to prove this is the same as n gamma delta. This is what I want to prove. Okay, so far I can easily do this using one of the most radical of my four relations between all this stuff. Namely, can I write it here? I will try. Alpha plus beta minus gamma minus delta is 0. And these four roots, to negative to positive, satisfy a certain condition. And I write n alpha beta, n negative gamma negative delta, plus n negative gamma alpha, n what remains? Beta negative delta, n beta negative gamma, n alpha negative delta is 0. And the same with primes, because I have everything with primes. So n prime, alpha prime, beta prime, but these two things are the same. N prime plus, and I need to write the same things with primes everywhere. But now let me say, these additional things here and here are both known to us. We know enough about them. Every n here contains a positive and negative root. Absolutely. Unlike the first summand. So in all cases, the sum of this is either zero, or, which is also possible, a positive root or negative root, which, however, is before negative row in row. You understand that if you have a positive root and a negative root, then it will, if it's still positive, why not? Then it is only closer to this, right? So for all this part, we have inequality, even if we write primes here, because n's and primes are the same within the domain between negative row and row. So these two things are equal to each other, right? And this also equal to each other. And also is not zero. So n alpha beta is equal to n prime, alpha prime by definition. And is not zero, because alpha plus beta is a root. Yes, and this completes the statement, especially if we take into consideration some other things. So what we have proved? We proved that n negative gamma negative delta and n prime negative gamma prime negative delta prime is the same. We have some equality number 4, some identity number 4. We said that n alpha beta times n negative alpha negative beta is equal to something. This something certainly will be the same for the two root systems. Depends on the root systems. So if we have this equality for negative gamma negative delta, we also have it for gamma and delta. And this completes the proof of our theorem, and actually slightly more. I will say what more, but first questions about this. No questions, no answers. This is my very strict rule. Indeed. Questions? Yes, you have a question.
All the way on the right, it says E on the upper board. On the upper board.
Oh!
It says E row, E prime row. Yeah, I can't read that. NH, E prime row is a
arbitrary if a row is not simple by default. Arbitrary, yes, arbitrary. Excuse me. More questions. So I see you understand my handwriting better, which I appreciate. Now, when I say that actually we have more than we stated, what do I mean? I mean one simple thing. I mean that actually whenever we have a map H into H prime, which homomorphism of H into H prime, which establishes isomorphisms between roots, then it can be extended to an isomorphism between G and G prime. H and H prime are subalgebras of G and G prime. We already have this isomorphism between H and H prime. So I state that we already also have this isomorphism can be extended. If two root systems are isomorphic, if this so we have an isometry between H and prime and so on. So better to say the root systems are isometric. Is the isometry unique? You remember my examples. And you certainly could observe that the root systems are very much possess sort of ample symmetry. There is a group of symmetries of a root system. Do you know how it's called? You know? Oh, you all know. Wile group. It has a definition. Slightly different with what I say. For every root, say alpha is a root. There is root negative alpha. Consider the orthogonal, the plane orthogonal to these two roots, and consider the symmetry, the reflection in this plane. It takes alpha into negative alpha into alpha, but also it takes roots into roots, and it is very, very, very easy to understand. These symmetries generate a group. There exists actually in algebra a beautiful theory of groups generated by reflections. Know something about that? Well, mostly belong to Coxeter, yes. Mostly belongs. This is the thing. Mostly belongs to Coxeter. There is a classification of such groups, and a Wile group is a group like this. There are groups, however, which are generated by reflections, which are not Wile groups for any Lie algebras. This classification is actually contains a lot more. There are different definitions of the Wile group. Different definitions of the Wile group, and for classical Lie algebras, it is very easy to specify the group. Actually, I can maybe even do something today like this, because when we will consider this classical. This is my next subject today. But yes. But first, let us consider the most obvious symmetry in the root system. A symmetry which takes alpha into negative alpha for every alpha. Also an isometry. So there exists an isometry. So G and G prime is the same algebra. Is the same. H and prime is the same, but the isometry is not the identity, but rather the maybe it is an element of the Wile group. But I prefer to consider this particular thing, just the reflection in zero, just alpha goes to negative alpha. Then there exists an involution, a map of G into G, whose square is the identity, right? Which is defined by this condition that alpha is mapped into G. Alpha is mapped to negative alpha. So in particular, G alpha and G negative alpha, which are very different one-dimensional subspace of my space, correspond according to this involution. This involution is not just -1. For example, for the Lie algebra GL, well, SL if you prefer to have simple Lie algebra. Can you guess what it is? No, you prefer that I say this. I would have said that this is the transposition. If it were true, it's almost true. It is negative transposition. So every simple Lie algebra has a very special map, self-maps, involution, which corresponds to this negation of the roots. Then I want just to add one thing, which I will not develop into anything else. We can additionally assume that the numbers n, the numbers n are actually invariant with respect to this involution. We can, in addition to all our equations for n's, we have 4 conditions. We can add one more. which can be formulated simply as n alpha beta is equal to n negative alpha negative beta. This doesn't follow from anything, and actually cannot follow from anything, but it is possible to achieve by multiplications of our E alpha by something. I will not say by what. It's very easy to say. Simply we compare E alpha and E negative alpha, and they should correspond with respect to our involution, which makes them more or less unique up to the sign. So there exists this more convenient, better basis in the Lie algebra, beta E alphas, which actually makes the choice of n alpha beta almost unique. Then we will have a system of 5 equations, not 4. And the system can be solved. The basis which we are speaking of is called the Weil basis. These numbers also probably have some name which I don't remember. And this is a way how to construct a simple Lie algebra if we have the root system. And as I said to you last time, actually these numbers n will be not just complex numbers. They will be all integers, which shows that actually we can apply this construction for Lie algebras over any field, including actually fields of finite characteristic. The numbers n alpha beta fully determine the structure of a Lie algebra. So this is all about this. And I have a last thing regarding the classification of Lie algebras, if you don't have questions about this. My last thing is, we have Dynkin diagrams for series and 5 exceptional diagrams. You remember that. So I want to say that for every diagram from this set, there exists a construction of a simple Lie algebra, which have this system of roots. These constructions are well known and deserve the name classical for the 4 series. Actually, they deserve this name and they have it because the Lie algebra which correspond to these 4 series of Dynkin diagrams are called classical Lie algebras. Let me observe all of them. AR. R dots with this system of edges. All edges are single. So we have R simple positive roots, the same length, and the angle between 2 adjacent roots is 120 degrees. All the other are orthogonal to each other. I say that the corresponding Lie algebra is S, L, R plus 1. Now why? SL plus R, you know what it is. So R plus 1 times R plus 1 matrices, complex matrices with 0 trace. The Cartan subalgebra is this. Diagonal matrices. The sum of lambdas is 0. Now it is well known, we discussed it and maybe even used. We know actually all the roots and all the root spaces. The roots are lambda I minus lambda j, where I and j two different numbers. Well, the same also. This is, as you understand, a linear function on this Cartan algebra. And the corresponding root space is generated by the one element matrix which has 1 on the intersection of ith row and jth column. These are roots. Now, positive or negative. Very much this is, I didn't say one thing. The inner product in this space is the usual inner product. It is almost true. I mean that certainly if you take the inner product, which is generated by the adjoint representation, as usually done, then the corresponding form will be proportional to the usual inner product, but not precisely this. It is better to take a different representation, and then the forms will be proportional. The most obvious representation of the Lie algebra cell R plus 1 is its action in the space C R plus 1. In this case, the trace is simply the trace of a matrix, right? And then it is very clear that the trace of product of these two matrices is simply the dot product of the corresponding diagonal vectors. So the usual Euclidean structure in this R-dimensional space, which is plane, a plane in the R plus 1 dimensional space, plane where the sum of coordinates is equal to 0. Now, next thing, positive roots. Simply I take lambda I minus lambda j with I greater than j. Then this, I call this root positive, and the opposite root negative. Very obvious. And then the simple positive roots are lambda 1 minus lambda 2, lambda 2 minus lambda 3, and so on, lambda r minus lambda r plus 1. There are r of them. Every positive root certainly is a linear combination, rather a sum, of several simple positive roots. Simply take a subset of this, some part going in row. Then the sum will be lambda I minus lambda j, right? Where I is r, excuse me, doesn't correspond to each other. Let me say I less than j. Simply to have this. Now it is very clear that if you take these vectors in this space, then the inner square of this will be 2. The inner product of these two will be negative 1. The inner product of two roots not next to each other will be 0. This precisely corresponds to this diagram. I sort of don't know what else to say. The while group, I will not give the specifics. I will include some exercises. But this is simply the group of permutations of lambdas. It is a very obvious thing. If you switch lambda I and lambda I plus 1, which precisely corresponds to one reflection, then this corresponds to the simple transposition in the set of roots. And this transposition generate the while group is generated actually by reflections defined for simple positive roots. Also very easy to understand. Yes, so this is AR. Next thing, very much non-alphabetically. I prefer to take DR. the thing. I state that the corresponding Lie algebra is S O, or simply O to R. SO to R. What is this? This is the Lie algebra of all skew-symmetric matrices of the order to R, right? Now I state that the best possible Cartan algebra is the following. I write 0, 0, lambda 1, negative lambda 1 here, 0, 0, lambda 2, negative lambda 2 here, and so on. 0, 0, lambda r, negative lambda r here. It's very much skew-symmetric matrix of order to R. And there are different ways to understand that actually this is Cartan subalgebra in this algebra. I know two ways. First, just to say it, and this is very convincing. Second, you see this matrix, even if you don't believe, actually also have eigenvalues. The eigenvalues are not real, right? The eigenvalue of the upper block r plus minus square root of lambda I. But still, if all lambdas are different, then all the eigenvalues are different, right? From this, simple complexification shows that this must be a regular element in our Lie algebra. I say complexification, no, it's a complex Lie algebra. I forgot about it. So we have a complex Lie algebra of all skew-symmetric matrices. And this is generalizable, actually. And as such, it has, if all lambdas are different, then, well, different, I say plus minus difference, and no lambda I is equal to negative lambda j. Then the square, yes. Then actually the eigenvalues of this, all the eigenvalues of this matrix are different over the complex field. And this is a regular element, so definitely, and it is very obvious that only elements like this commute with this matrix. It is very simple to understand, very easy to understand. You can do this again, making this matrix, making this makes the diagonal by changing the basis change. So this is true. That this is Cartan subalgebra. And now, what are the roots? First, root spaces. Root spaces are very. It's easy to understand what the root spaces are. I could say that they are one-element matrices, but rather they are two-element matrices. So for some I and j, we have the ij entry 1 and negative I negative j, and ji, excuse me, and ji entry negative 1. It is a skew-symmetric matrix, and obviously it is a root vector. That is, its commutator with any matrix like this will be the same matrix with some coefficient. Now, what are the roots? Very obvious. The roots are plus minus lambda I plus minus lambda j. Where I and j are different. Now I make the remaining statement without, so they may be regarded as exercises. I want to show all the simple positive roots. From this it will be clear which roots are positive, sums of single positive roots, and which was a negative. Lambda 1 minus lambda 2, lambda 2 minus lambda 3, so on, lambda r minus 1, no lambda r plus 1, minus lambda r, and also lambda r minus 1 plus lambda r. This is my system of simple positive roots. And it is very clear, again, the inner product is the usual inner product in this space of dimension r. And it is very clear that what? First, the length of every vector is the inner square of every vector is 2. Second, these vectors, this and this, this and next, this and next, have certainly inner product -1. But also we have this, lambda r minus 2 minus lambda r minus 1. And this also have inner product -1. See it? This inner product -1, this, and so on. We have precisely that diagram. This is dr. Everything remains to you, in particular, what is the Weil group is very easy to understand. It's very easy to understand. Now there are two more letters, B and C, right? Good. BR. And this. It is O to R plus 1. Why so? Look, in this matrix of the order to R plus 1, again we can do this. Here we have 2 rows, 2 rows, 2 rows, and 1 row. Again, we can write lambda 1 minus lambda 1, lambda 2 minus lambda 2, and lambda r minus lambda r. And zeros on the diagonal, including this spot. And what we have here, we have an r-dimensional subspace. And again, it is very easy to understand that it is a Cartan subalgebra. That actually this element, if all lambdas are different, plus minus different, so no lambda is equal to negative other lambda. If all the lambda are plus minus different, then this matrix is a regular element of order y. What are the eigenvalues? The eigenvalues with Cartan permission are again plus minus square root of lambda 1I, plus minus square root lambda 2I, and so on, and also 0, which is not equal to any other eigenvalues, right? So this is a matrix with all eigenvalues different, from which it is very easy to deduce this is a regular element, and in particular this is a Cartan subalgebra. Now, what are the roots? And the roots are plus minus lambda I for all I and j, not equal to each other. And also plus minus lambda r, plus minus lambda k. Because also we have, you know, we have one-dimensional root spaces here. And they certainly know only lambda, so this is true. If so, if say we have here, then the corresponding root will be lambda 2. yes. And here minus lambda 2. Yes, so this is the set of all space of all set of all roots. And certainly lambda I minus lambda j with I less than j, and also plus lambda r. These are simple positive roots, and it's very clear that the length of lambda r is smaller than the length of all the rest, right? It's inner square root of 1, not 2. And everything is true regarding the angles. See that? All the inner products are negative ones if we take two differences in a row, and also lambda r minus 1 minus lambda r and lambda r also have the inner product negative 1. So this is BR. And now CR. Certainly this algebra, this Lie algebra, I don't know, maybe I will also say this next time, because this Lie algebra definitely deserves more than 2 minutes and 40 seconds, which I have. CR. Do you know the name of this, what this algebra is? Some of you probably know. What is this? Symplectic, yes, SP. What is this? First of all, symplectic group. Orthogonal group, if you don't know, is the group of transformation which preserve the canonical, unique, actually non-degenerate, symmetric bilinear form in the space. But also there are non-degenerate skew-symmetric bilinear forms. It is possible if the dimension of space is even. There is such a form. We have a basis in an even dimensional space. Let me write E1, let be R, F1, Fr, and the inner product is skew-symmetric of EI, Fj is delta Ij, and the inner product of I, Ej, and negative will delta J if you switch the order, is symmetric. And this is 0 for all I and j, including. Now we can consider the group of matrices which preserve this form in the usual sense, and also the corresponding Lie algebra. This Lie algebra, it is very easy to understand. It is not just skew-symmetric matrices. It is the following. Two R cross 2R matrix. A here. A, T here. B here, and C here, and B and C both are symmetric. So we consider matrices with these properties, and they form a Lie algebra. The commutator of such matrices has all these properties. And this Lie algebra, which has the same dimension, actually, as O to R, easy to calculate the dimension, the same dimension as O to R. And well, I probably will say something about, I didn't plan to do this. I will say something about this Lie algebra next time. It is very easy to write everything, Cartan subalgebra, roots, and to find that the corresponding Dynkin diagram is the Dynkin diagram CR. I will say some more about this in the first 5 minutes of my next lecture, and I will spend maybe 3 more minutes to discuss the exceptional Lie algebras. Thank you.